Title of the talk is Mapping London Air Pollution at Street Level in Real Time with the world's first large-scale network of low-cost sensors. And my name is Matthew Johnson. Jens Christian asked me to do a very short introduction, and so here's a little biography. I'm from a town called Owatonna, Minnesota. There's a famous bank, the Farmers National Bank, in my hometown. I did my bachelor degree in chemistry, specializing in inorganic chemistry at Macalester College in St. Paul, Minnesota. I have a PhD in physical chemistry from Caltech in Pasadena. I then went to work at Max Lab in Lund, Sweden. It was Max 1 at that point, and I was doing infrared spectroscopy at Max Lab. And then I started working at the University of Copenhagen and have been an assistant associate and now full professor at the University of Copenhagen. And one of the things that we've done here is to invent things. And this first invention was for a method of cleaning air. And you can see that this was filed 2009. This patent was granted in 2017. It resulted in the formation of a company that's called Infuser, and you see that here. Infuser has raised something like 150 million Danish crowns from domestic and foreign sources since it was founded in 2012. And it's led to the formation of many other companies, either directly or indirectly. And I have those here. The first spin-off company from Infuser is called Air Labs, and Air Labs is working with air filtration and with sensing. This has led to the development of the company AirScape, and I'll tell you about our collaboration with AirScape today. And also a company called Dev Labs that is focused on making these devices. We also have companies that are working on removing pollution from air. There's Domosphere. There's ambient carbon focusing on methane. There's now a company called Epic. There's Zymoscope that is looking at carbon dioxide sensors. Sterisafe working with whole room decontamination. And Expuris in Germany, which is also working with air purification. And so just this one breakthrough has then led to the formation of many additional startup companies. And I'd like to tell you about one of these projects today. We call it AirScape. It's the world's first high-density network of low-cost pollution sensor nodes. And we've installed this network in the Borough of Camden in London. And there's been many people involved with setting up this project. Of course, AirScape. We have support from a project called Actress in Denmark for research infrastructure in Denmark. We're working together with the Big Data Center for Environment and Health, Bertha, at the University of Aarhus. We've had support from the University of Surrey in the United Kingdom, from Air Labs, Dev Labs, a group called the Camden Clean Air Initiative and the Camden City Council, and of course, from the Department of Chemistry at the University of Copenhagen. And this is based on these low-cost sensors, and I have one of these here. This is an earlier generation. But basically, you can see here some of the different sensors. These are electrochemical cells, and they're able to measure oxidizing gases. And so these two that we have right here are measuring ozone and nitrogen dioxide. And one of the features of this is that they have a very fast time response. They're very cheap, but they require some calibration. And so one of the things that we have to pay attention to is how we calibrate the information coming from these sensors. Also inside this box, there's a particle sensor, and that's based on laser scattering. And all of these sensors are gathered together into a node, and the node has a microprocessor. It has power supplies for the sensors. There are amplifiers, and it also takes care of communication. And so what we're doing is gathering all of this data, and then it has a SIM card. And so we're using the mobile phone network to upload that data onto the cloud. And then on the cloud, we can do processing, and we're able to display the data. And I'll show you some of that data here today. Now we go back to the talk, and I can tell you a little bit about why we should think about air pollution. And here's a figure showing disease by risk factor. And you can see that the number one risk factor is high blood pressure. After that, at number 2, we have air pollution. And air pollution is killing many people every year. Something like 7, 8, or 9 million deaths every year, depending on how you count it exactly. That's more people, for example, than have been killed in the COVID pandemic. So we believe it's a very significant problem and something that people should definitely pay attention to. Air pollution has been a cofactor in the pandemic. And part of the reason is that it causes damage to the respiratory tract lining, making people more vulnerable to infection. And it also suppresses the immune system. So you can catch things more easily, and the things that you catch can result in worse disease. And there's different statistical values linking COVID mortality to exposure to air pollution. For example, in Europe, 19% of the COVID cases, the mortality is linked with air pollution. So a very significant problem. There's growing recognition of the importance of air pollution and of the health impacts of air pollution. My colleague Ola John Nielsen is teaching a course on air pollution and health that will be starting in just a couple of weeks. In response to these concerns and the latest research regarding the health impacts of air pollution, the World Health Organization has slashed its recommended thresholds for exposure to air pollution. And you see here that the recommended exposure threshold for PM 2.5 has been reduced by half, from 10 to 5 micrograms per cubic meter. And then nitrogen dioxide has been reduced from 40 to 10 micrograms per cubic meter. And there are many health impacts associated with exposure to air pollution. It could be cancer, it could be heart disease and high blood pressure, it could be suppression of the immune system. There are also short-term effects like headache and mood problems and trouble concentrating. And one of the things that we see with these low-cost sensors is the short-term variation in air pollution. These are some of the short-term effects of exposure to intense or acute air pollution. There's psychiatric disorders, there's triggering of asthma, there's pneumonia symptoms, and stroke are all associated with short-term acute exposure to air pollution. So there are both long-term effects and there are short-term effects. Now, the traditional way of looking at air pollution is using fixed monitoring stations. And Denmark has a little bit over a dozen of these monitoring stations. We have one of them on the roof of the building next to me at the H.C. Ørsted Institute. And there's also one down by the City Hall. These have instruments, you have a building, you're sampling the air and looking at nitrogen dioxide, PM, particulate matter, ozone, sulfur dioxide, carbon monoxide. And these require real estate and a building and electricity, and you need technicians in order to calibrate these things. And they're very expensive. And in comparison, these low-cost nodes are 1/100th of the cost, perhaps less than 1/100th of the cost. And the idea then is that we might be able to get much better information using these low-cost sensors compared to what you can obtain using the fixed monitoring stations. There are some challenges there. And of course, the low-cost sensors have a lower data quality. And one of the first distinctions that you come across is that measurements with the low-cost sensors cannot be used to enforce regulations. So you do need a calibrated instrument, very properly controlled, in order to enforce legislation that we have regarding air quality. But the low-cost sensors offer some advantages. One of them is a high time resolution. The time resolution of this AirNode is about 1 minute. The monitoring stations, in comparison, might put out a data point every hour, perhaps every half hour, depending on exactly which station it is. The other thing is that because of the low cost, you can afford a lot of measuring locations, and you can increase the spatial density of your monitoring locations. So for this network in London, we've increased the spatial resolution by a factor of 100 relative to the network that was in place before, a very sparse network. All right, there's a lot of research going on where they use these small sensors in order to figure out where people are exposed to air pollution throughout the day. There was a project where 250 school children in London were given backpacks, and then they went throughout their day, and you could see if their parents were smoking. You could see when dinner was being made at home. You could see if the school, often schools don't have very good air quality or ventilation in the building. And one of the risks that they found was that pupils were exposed to about 5 times higher concentrations of harmful nitrogen dioxide on the school run than they were at the school itself. And all of this just shows that the local environment really determines your exposure to air pollution. And if you have a monitoring station on the top of a building, like we have here, that doesn't tell you what the pollution level is at the side of the street, where you might be spending a lot more of your time, or inside of a building, where you also might be spending a lot more of your time. So we see a role for the low-cost sensors in helping to characterize a lot of these detailed environments. Now, what have we done here? In the third quarter of 2021, we built these AirNodes. We built them here in Copenhagen. We calibrated them at the University of Copenhagen, and we delivered them. And we started to install them in the Borough of Camden in London during the first quarter of 2021. That was just a few units that were being installed at the time. We completed the entire network of 225 AirNodes in the first quarter of 2022. And there's a lot of logistical problems involved with getting all of these AirNodes installed. I could talk all day about the problems that you encounter in installing all of these. But basically, we were in a position to go live in the second quarter of 2022. When we went through the calibration, we found that we could do that much more quickly using a hybrid method. So if you use a chamber in order to intercalibrate your node with a reference monitor, you encounter some problems. One of the things is that the air in the chamber is not the same as the air in a town. It could be contaminated with glue or with whatever you have in your laboratory. We found much better results by drawing air in from outside into an insulated duct and then spiking that air using different pollutant gases. And then we could intercalibrate the behavior of the AirNodes with the reference monitors. And when we did that, we got a good initial calibration. We could then send them out into the field and start to take data. Here's an example of one of these intercalibrations. And basically the bottom line, we changed these concentrations of nitrogen dioxide and of ozone. We did that in the laboratory here on the 5th floor. You find that this hybrid method is fast and effective and allows you to come within the range required for indicative measurements as defined by different standards that are available. We then did a field study where we installed these sensor nodes in the parking lot at the University of Surrey. And you can see that the cables are then going in through this little window and coming into the laboratory, where we could then compare the results with calibrated instruments. And these are some of the calibration plots that we saw from that. In every case, for PM2.5, ozone, carbon dioxide, and nitrogen dioxide, we found very good R-squared values indicating the correlation was excellent. Now here we have the record, the time record from one of our co-locations. This was on Euston Road in London, so a very polluted location in London. And one of the things you can see is that given the old World Health Organization exposure limit of 40 micrograms per cubic meter of nitrogen dioxide, the city might not be in violation. But given the new exposure limit of 10, you can see that we're often over the exposure limit. And this means that that extra pollution that you have at street level that you might not be measuring using the regional monitoring network could be the extra straw that breaks the camel's back, that puts you over the exposure limit. So we think that we're measuring something very important using these low-cost sensors. Now, we started to see some very interesting things. And one of these is that we put carbon dioxide sensors into all of the nodes that are installed in Camden, in London. And then there was a tube strike on March 1st, 2nd, and 3rd, very soon after we had these sensors installed. And that meant that everybody had to use road traffic. And so road traffic just skyrocketed during these days of the tube strike. People were taking taxis and buses in order to get to work. And we saw carbon dioxide increase across the borough from an average of 430 parts per million in the city to 442 and up to even 530 during some conditions during the time of the tube strike. So we're seeing emission of carbon dioxide from local transportation in real time. We were also able to see the increase in nitrogen dioxide because a lot of diesel engines are being used in London. The non-strike average of NO2 is something around 35 micrograms per cubic meter. That's a very high level to begin with. During the strike, that increased to 58 micrograms per cubic meter, a 66% increase. The maximum values during the strike were anything between 60 and 100 micrograms per cubic meter. So extremely high levels of nitrogen dioxide. We also saw elevated PM 2.5. These are the particles that are able to deposit into your lungs and introduce foreign, often toxic chemicals into your system. Here, the non-strike average was around 6 micrograms per cubic meter, and during the strike, that increased to 25 micrograms per cubic meter. All right, we also saw an event where all of the carbon dioxide across the borough increased by about 100 ppm all throughout Camden. And we really scratched our heads in order to figure out what could be causing that increase in carbon dioxide, which was not associated with an increase in particulate matter PM or with nitrogen dioxide. So it must be a very large event. And we thought maybe, pollution coming in from Europe that might cause this. I did something called a back trajectory, where you can figure out where the air is coming from. And the air wasn't even coming from anywhere in Europe. The air was coming from the North Atlantic. And I thought that was kind of strange. I was talking with a researcher from Cork. I said, the air is coming from Iceland. What could it possibly be? And that was the key. The air was coming from Iceland. It turns out that the largest volcanic source of carbon dioxide in the northern hemisphere is a volcano on Iceland. It's called Katla. It sits beneath a glacier. And so we believe that there was simply a plume of carbon dioxide that went up over the Atlantic, took a couple of days to get to London, came down, and then we were able to see that throughout the network. So we see a lot of things. We see very local effects, and we also see some global effects. Now, here's an example. We have a PhD student named Louise. She's done a lot of work on this paper, and we installed a network of pollution monitors in a small town in Staffordshire called Newcastle under Lyme. And we also installed anemometers that detect the wind speed and the wind direction at the same time. And then you're able to do kind of an analysis method where you can correlate the pollution levels with the wind speed and the wind direction. This allowed us to identify one of the local sources of pollution, which happened to be parents who are driving their children to school, and maybe they're sitting there in the Land Rover, the engine is idling, and you're emitting nitrogen dioxide, which we see with the monitors. Using this network, we're able to differentiate between local pollution and regional air pollution. And we would expect different signatures from local and urban air pollution and regional air pollution. For example, if you have a very large air mass that is polluted, such as the volcanic plume arriving from Iceland, you have a very slow increase and a very slow decrease. But if your source is local, such as a truck where the engine might not be tuned correctly, you'd have a spike of pollution, a very rapid change in the pollution. And this means that you can use a mathematical method called the Fourier transform in order to find the frequency of the change in the pollution concentrations. And here we see an example showing nitrogen dioxide. You see some high frequency peaks that you don't see when you're looking at particulate matter. And the reason for this is that particulate matter is often a regional air pollutant, and nitrogen dioxide can often be associated with local sources. Here's another example of this where we just took data from 3 different stations, Lady Bower, Stoke-on-Trent roadside, and then an urban background station. And you can see that the background station, not close to any pollution sources, is only showing the low frequency air pollution. And then when we go to the more urban settings, we start to see higher and higher frequency components in the air pollution. And these sensors might have problems with calibration or with baseline drift. We always try to do our best to calibrate the sensors and account for that. But even though the baseline might not be accurate, the change in pollution is very accurate. And so we were able to see these changes very well, and we get some valuable information from the low-cost sensors that you simply cannot see using the regional monitoring network. Doing a lot of mathematical heavy lifting, we were then able to find out the sources of the air pollution at that location in Staffordshire. And we found that for PM 2.5, the regional sources were dominant, and for nitrogen dioxide, the local sources were dominant. And I think that's a very significant finding, because that means that your exposure to nitrogen dioxide is under local control. And so if you were to move the road and the traffic away from the school and the places where people are living, for example, or change traffic patterns or change the vehicles that are allowed in the town, maybe you would install a low emission zone, you can see clearly that that would have an effect to reduce people's exposure to air pollution. And there's different statistics here that we found from that. But one thing that I wanted to be sure to have time to do is to have a little tour where I just show you AirScape. And so if we go to Google here, this is just a browser. I'm going to type airscape.ai and hit enter. And we've made all of this data publicly available from London. And so here you see a map of air pollution, and it happens that right now, the air quality in the Borough of Camden in London is quite good. We can look at the history, and then we see, a 5-minute average or a 1-hour average or a 6-hour average. And then this is last night. We have yesterday evening. We see a little more pollution starting yesterday evening. Air pollution might be building up over the day. And you can go back in time. Maybe you have a hot spot of air pollution coming in here. Or we could see little bursts of air pollution. And so if I go back, you can see sometimes little locations just pop up. And so here, this looks like it was 7:55 this morning. This is live data. I could zoom in on that location, and you're seeing that more pollution appears, or more measuring sites appear as we go higher in spatial resolution. And we just click on that sensor. So that's 40 radon street. And the air quality index shows a burst of something. We could look closer and try to see what that pollution is. Looks like it's not PM 2.5, it's not ozone, but it's nitrogen dioxide. And it looks like it was going up to 38 micrograms per cubic meter at that location at that time. And so this might have been maybe a heavy duty vehicle, a diesel truck that goes by that is emitting pollution. At one point, we found a bus that seemed to be going by every 20 minutes. So every 20 minutes, we would see a peak in air pollution. One of the other things you can see is that as you go to higher integration times, so longer averaging times, the air quality index gets worse. And this is because a short exposure to a high level of pollution might not be associated with a tremendous amount of excess risk. But if you have a long exposure to the same level of pollution, the risk goes up. And this is reflected in the WHO recommendations and other kinds of recommendations that you don't want to have a long exposure to air pollution. And we believe that growing awareness of the air pollution that you can find in cities will empower people to start to make better choices about where they spend their time. Maybe they would take a green route to get to work or choose a different means of transportation in order to avoid the air pollution. All right, I will go back to the presentation and show you some last slides. And then I think we'd like to leave some time for questions. And the final thing to show you here is just a very interesting study we did using the Google car. So this car was outfitted with a lot of different kinds of air pollution monitoring equipment. It had formerly been used to take pictures of the streets around Denmark. And then we could intercalibrate the nodes with the instruments and also check the behavior of the network. And one of the interesting things we found is that you often have very large changes in air pollution over small spatial scales within the city. And here we're just seeing over something as small as 20 meters, the nitrogen dioxide levels could be changing by a factor of 10. And so we believe that this high resolution is very important in order to get a picture of people's exposure to air pollution. Here's another small study we did called the vertical study, where we're just looking at the air pollution levels at different altitudes in relation to this street, which has a lot of traffic in the morning outside of our institute. And we've been using different algorithms to figure out the traffic levels and correlate this with noise and with air pollution. And it was really a pleasure to give you this short talk about our project.